In this episode, we're going to connect two ideas that beginners often keep separate in their minds: vulnerabilities and attacks. A vulnerability is a weakness that exists in a system, but it becomes meaningful only when an attacker can use it to achieve a goal, like reading data, changing behavior, or gaining access. An attack is the sequence of steps an attacker takes to exploit weaknesses, and those steps often depend on common patterns that repeat across many technologies. Today, we'll focus on several of the most important patterns you'll see again and again: injection, cross-site scripting, XSS, server-side request forgery, SSRF, misconfigurations, and secrets exposure. The goal is not to turn you into a programmer overnight, but to give you a defender's understanding of what these attacks are, why they work, and what clues they tend to leave behind. When you understand the logic of these attacks, you can reason about risk, recognize symptoms, and recommend mitigations without needing to memorize every technical detail. Before we continue, a quick note. This audio course is a companion to our course companion books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyber.author.me in the Bare Metal Study Guide series. A good way to begin is to understand why these specific attack types matter so much. They are common because they exploit fundamental design mistakes that are easy to make and hard to fully eliminate, especially in large systems. They also tend to produce high-impact outcomes because they can lead to data exposure, account takeover, remote control of servers, or access to internal networks. Another reason they matter is that they often chain together, meaning one weakness enables the next step, and the overall attack becomes much stronger than any single issue alone. Beginners sometimes think attacks are always about malware, but many of the most damaging incidents are about abusing normal application features in unintended ways. Instead of breaking in by force, the attacker convinces the system to do something dangerous by speaking its language, like sending carefully crafted input. This is why learning these patterns is valuable even if you never write code, because your job as a defender is often to spot risky designs and advocate for safer patterns. When you can explain how an attack works in plain terms, you can help teams fix the right thing rather than chasing symptoms. Injection is one of the oldest and most important vulnerability categories, and it begins with a simple idea. A system takes user input and accidentally treats it as instructions. Many systems build commands or queries by combining fixed logic with variable input, and if that variable input is not handled safely, an attacker can reshape the command. The classic example is database queries, but injection can happen in other contexts too, like operating system commands, directory paths, or structured data formats. Beginners sometimes assume injection requires special hacking tools, but the root cause is often a simple programming mistake where the system fails to separate data from code. When that separation fails, an attacker can influence what the system executes, not just what it stores. The impact can range from reading unauthorized data to changing records to gaining full control over a backend system. Injection matters because it turns a normal feature, taking input, into a control channel for attackers. From a defender's perspective, the most useful way to analyze injection is to ask what interpreter is being tricked and what boundary is being crossed. The interpreter could be a database engine, a command shell, a template engine, or another component that reads instructions in a structured language. The boundary being crossed is the one between user-controlled data and system-controlled logic. When input is inserted into the logic without safe handling, that boundary dissolves. Beginners often think validation means checking for bad characters, but attackers can bypass simple filters, and filtering can break legitimate input. Safer approaches are about structured handling, where user input is bound as data in a way that the interpreter will not treat as code. Another important defensive insight is that injection often leaves clues in logs, such as unusual characters, unexpected query patterns, or error messages that reveal the system is trying to interpret input as instructions. When defenders analyze injection, they look for both the attempted payload and the system's response, because error behavior can show whether the system is vulnerable even if the attack did not fully succeed. The logic is to detect not just compromise, but exposure. Cross-site scripting, or XSS, is a different kind of injection that targets the user's browser rather than the server's database, but the underlying theme is the same: unsafe handling of input and output. In XSS, an attacker causes a web page to include malicious script content that runs in the victim's browser in the context of a trusted site. That matters because the browser believes it is interacting with the trusted site, so the script may be able to access session information, perform actions on the user's behalf, or modify what the user sees. Beginners often assume XSS is just annoying pop-ups, but modern XSS can lead to account takeover, data theft, and manipulation of transactions. The key to understanding XSS is that the attack lives in the gap between what the server sends and what the browser executes. If the application reflects user input back into a page without proper output encoding, or stores it and later displays it to others, the attacker can inject script that becomes part of the page. The damage depends on what the script can access and what the user's privileges are, which is why XSS is especially dangerous when it hits administrative interfaces. Analyzing XSS as a defender involves thinking about trust boundaries and the browser's same origin behavior. The browser uses the site's origin as a trust anchor, meaning scripts from that origin are treated as belonging to the site. If an attacker can run script under that origin, they can often do things that the user could do because the site trusts the user's browser session. Beginners sometimes think the solution is to block all script, but web applications depend on script, so defenses focus on preventing untrusted input from becoming executable. That includes proper output encoding, careful use of templating, and limiting risky behaviors like building HTML directly from user input. Another key idea is reducing the impact even if XSS happens, such as limiting what session tokens can be accessed and reducing the power of scripts. From a monitoring perspective, XSS can be hard because it happens in the browser, but defenders can still look for suspicious patterns, unusual parameters, and signs of stolen sessions being used from new contexts. The important beginner takeaway is that XSS is not just a website bug. It is a way for attackers to turn your users into remote control channels inside your application. Server-side request forgery, or SSRF, is a modern favorite among attackers because it exploits the server's ability to make network requests, often to fetch data or integrate with other services. Many applications legitimately reach out to other resources, such as retrieving an image from a URL, calling an external API, or validating webhooks. SSRF happens when an attacker can influence those outbound requests, so the server makes requests the attacker chooses. This matters because servers often have network access that external attackers do not, such as access to internal services, metadata endpoints, or administrative interfaces. Beginners sometimes assume the server is just a passive responder, but in modern architectures, servers are active clients as well, constantly talking to other systems. If an attacker can redirect that client behavior, they can use the server as a proxy into the internal environment. The impact can include reading internal data, accessing cloud metadata, discovering internal services, and in some cases escalating to deeper control. SSRF is a good example of how attackers abuse normal features rather than exploiting a classic memory corruption bug. To analyze SSRF, defenders think about what request capability the application has and what constraints are supposed to exist. The application might allow users to supply a URL, an address, or a reference that the server will fetch, and the intended constraint might be that the server fetches only certain approved resources. If validation is weak, an attacker might supply internal addresses, loopback addresses, or unexpected protocols to reach internal systems. Another key factor is what the server can access, because SSRF is only as powerful as the server's network position and identity. In cloud environments, access to instance metadata can be especially sensitive because metadata can sometimes reveal credentials or configuration details. Monitoring for SSRF often involves watching for unusual outbound requests from application servers, especially requests to internal addresses that are not normally contacted or to metadata like endpoints. Beginners should see SSRF as an access pivot, meaning it turns a web app into a bridge, and the defense strategy is to restrict what the server is allowed to reach and how user-controlled input influences those requests. When you understand the pivot concept, SSRF becomes less mysterious and more predictable. Misconfigurations are often the most common vulnerability category in real environments because they are not a single bug, but a pattern of mistakes in how systems are set up and managed. A misconfiguration might be a publicly exposed storage bucket, an admin interface left open, overly permissive identity roles, weak default credentials, or a service running with unnecessary privileges. Beginners sometimes assume misconfigurations are minor because they sound like accidents, but accidents can be catastrophic when they expose sensitive data or grant powerful access. Misconfigurations also scale because templates and automation can replicate the same mistake across many systems. Another reason misconfigurations matter is that attackers often scan for them automatically because they are easier to exploit than complex application bugs. If a system is publicly reachable and misconfigured, an attacker might not need to exploit anything. They simply use the exposed feature as designed. Analyzing misconfigurations, therefore, involves understanding intended access boundaries and comparing them to actual settings, which is more about architecture and governance than about code. A defender analyzing misconfigurations focuses on where trust is assumed rather than enforced. For example, a cloud resource might be assumed to be private because it is used internally, but if it is configured for public access, the assumption is false. A role might be assumed to be limited because it belongs to a low-risk service, but if it has broad permissions, the assumption is false. Misconfigurations also have a life cycle because systems can drift over time as changes are made, so what was secure last month might be exposed now. Monitoring for misconfiguration-driven attacks often includes watching for unusual access patterns, such as unexpected public downloads, unusual management access, or sudden changes to permissions. Another helpful beginner insight is that misconfigurations often interact with other vulnerabilities because an injection bug might become far more dangerous if the service account has excessive permissions. So fixing misconfigurations can reduce the blast radius of many other issues, even those you haven't discovered yet. In that sense, configuration hygiene is a multiplier for security because it reduces how much harm any single weakness can cause. Secrets are the final focus area in the title, and they connect to almost every other attack type because secrets are how attackers turn access into control. Secrets include passwords, keys, tokens, certificates, and anything else that grants permission or proves identity. Secrets exposure can happen through code repositories, misconfigured storage, leaked logs, debugging output, or accidental inclusion in error messages. Beginners sometimes assume secrets are hard to steal, but in practice, attackers frequently find them in the easiest places because humans copy secrets into places that feel convenient during development or troubleshooting. Once a secret is stolen, the attacker often doesn't need to exploit anything else. They can authenticate like a legitimate user or service. Secrets are also powerful because they can persist, meaning a stolen long-lived token or key can remain useful until rotated or revoked. Analyzing secrets exposure involves asking where secrets are stored, who can access those locations, and what monitoring exists to detect unusual use of credentials. It also involves recognizing that secrets often enable lateral movement, because one secret can unlock another system, which can reveal more secrets, creating a chain reaction. From a defender's point of view, the most important thing about secrets is that they create identity, and identity is what controls access in modern environments. If a secret leaks, the attacker can often bypass many detection methods because their actions look like normal authenticated behavior. That means secrets attacks are sometimes discovered not by a malware alert, but by unusual login patterns, unusual data access, or unusual privilege use. Beginners sometimes focus on the moment the secret was leaked, but the more urgent question is whether the secret was used and what it enabled. This is why rotation and revocation are so critical, because they are the way you cut off the attacker's access once you suspect exposure. It also explains why least privilege matters, because if a leaked secret has minimal permissions, the attacker's options are limited. Secrets analysis is therefore not just about finding the secret. It is about tracing the permissions tied to it and the actions taken with it. When you think this way, secrets become a manageable risk rather than a constant mystery. To bring these concepts together, it helps to view them as different ways attackers cross boundaries. Injection tries to cross the boundary between input and instructions on the server side. XSS tries to cross the boundary between user content and executable script in the browser. SSRF tries to cross the boundary between external access and internal network reach by using the server as a proxy. Misconfigurations represent boundaries that were never properly set, leaving doors open by accident. Secrets exposure represents boundaries that were bypassed entirely because the attacker obtained the keys to the doors. These categories also frequently interact because an attacker may use an injection bug to access a secret store, or use SSRF to reach metadata that yields credentials, or use XSS to steal a session token that acts as a secret. Beginners should see this as an attacker's pathfinding exercise. Attackers look for the easiest boundary crossing and then build on it. Defenders respond by strengthening boundaries, limiting privileges, and monitoring for the patterns that indicate crossing attempts. When you understand the boundary crossing theme, you can analyze new vulnerabilities you encounter by asking, what boundary does this break, and what would an attacker gain if they succeed? To conclude, analyzing vulnerabilities and attacks like injection, XSS, SSRF, misconfigurations, and secrets exposure is about understanding how systems mistakenly treat untrusted input as trusted behavior. Each category has its own mechanics, but they share common themes: weak separation between data and control, overly permissive access, and hidden pathways that turn normal features into attack channels. As a defender, your job is to understand what these attacks enable, how they tend to show up in telemetry, and what practical mitigations reduce both likelihood and impact. You don't need to memorize every payload to be effective. You need to understand the logic that makes the vulnerability exploitable. When you can explain the boundary being crossed and the privilege being gained, you can prioritize fixes, improve monitoring, and communicate risk in a way that decision-makers can act on. That is the defender's skill, turning technical weaknesses into clear risk narratives and practical improvements that make future attacks harder.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.